Good day everyone, my name is Josh Kovic Fermana, a computer science student from Technological University of the Philippines, Manila. And in this video, I will be trying to solve a problem, particularly a Myhill-Nerode Theorem. What is Myhill-Nerode Theorem? The Myhill-Nerode Theorem is a fundamental result in the theory of formal languages that provides necessary and sufficient condition for a language to be regular. It connects the algebraic properties of a language to the computational power of finite automata. So let's look at the problem. We have our language. L sub 20 is equals to the input of epsilon, A, double A, and triple A. The description: a finite language containing only 4 strings. Use Myhill-Nerode theorem to determine the regularity. So let's try to solve the problem. First, let's understand the language. So we have the empty string epsilon, the string A, the string double A, and the string triple A. So let us construct the DFA. We have 4 states. We have 3 accepting states from Q0, Q1, Q2, Q3, and the reject state Q4. So the initial state is Q0, input empty string epsilon will return to Q0, input A will go to Q1, input A from Q1 will go to Q2, input A from Q2 will go to Q3, input A from Q3 will go to Q4, and input A from Q4 will return to Q4. The transition table. We have the state, the input A, and determine whether it's final or not. So we have 4 states again, the Q0, Q1, Q2, Q3, Q4. From Q0, input A will go to Q1, final, yes, because it is accepting state. From Q1, input A goes to Q2, final, yes. From Q2, input A goes to Q3, final, yes. Q3, input A goes to Q4, final, yes. From Q4, input A goes to Q4 again, final, no. The Myhill-Nerode relation analysis. So the rule. We say string of x is bodies with string of y, written as x is equals to y if for any ending string z you can think of. If x is followed by z, that is x times z is in our language. Then y followed by z, y times z must be also in our language. And if x times z is not in our language, then y times z must also not be in our language. Basically, whatever happens to x times z is the exact same thing must happen to y times z. If we can find even one z that breaks this rule, then x and y are not bodies. So let's try testing the second one. Is epsilon bodies with double A? So let's try adding double A as our ending z. Epsilon followed by double A is double A. Is double A in our language? Yes. Double A followed by double A is quadruple A. Is quadruple A in our language? No. So epsilon and double A are not equivalent. Let's try the third one. Is epsilon bodies with triple A? Let's try adding A as our ending z. So epsilon followed by A is A. Is A in our language? Yes. Is triple A followed by A is quadruple A? Is quadruple A in our language? No. So again, epsilon and triple A are not equivalent. So the fourth one is A bodies with double A. Let's try adding double A as our ending z. A followed by double A is triple A. Is triple A in our language? Yes. Double A followed by double A is quadruple A. Is quadruple A in our language? No. So they are not equivalent. So the fifth one is A bodies with triple A. Let's try adding A as our ending z. A followed by A is double A. Is double A in our language? Yes. Triple A followed by A is quadruple A. Is quadruple A in our language? No. So again, they are not equivalent. So let's try the last one. Is double A bodies with triple A? Let's try adding A as our ending z. So double A followed by A is triple A. Is triple A in our language? Yes. So in triple A followed by A is quadruple A. Is quadruple A in our language? No. Again, they are not still equivalent. So the equivalence classes, based on our tests, we've found this distinct group of bodies or equivalents. Group 1, epsilon is only bodies with itself. The group 2 is only bodies with itself. A is only bodies with itself. Group 3, double A is only bodies with itself. Group 4, triple A is only bodies with itself. Group 5, all these long strings are bodies with each other because adding anything to them keeps them out of our language. So we will be marking the pairs where one state is final and another is non-final states. We have Q0, Q1, Q2, and Q3 which are final, and Q4 which is non-final, so all pairs with Q4 are marked with X. Step 2, first round of marking. So for Q0, Q3, from 0, input A is equals to Q1. From Q3, input A is equals to Q4. Since Q1 and Q4 is marked, mark Q0 and Q3. So for Q1, Q3, Q1 input A is equals to Q2. Q3 input A is equals to Q4. Since Q2 and Q4 is marked, mark Q1 and Q3. For Q2 and Q3, Q2 input A is equals to Q3. Q3 input A is equals to Q4. Since Q3 and Q4 is marked, mark Q2 and Q3. Step 3, second round of marking. For Q0, Q1, Q0 input A is equals to Q1. Q1 input A is equals to Q2. Since Q1 and Q2 will be marked, mark Q0, Q1. For Q0, Q2, Q0 input A is equals to Q1. Q2 is input A is equals to Q3. Since Q1 and Q3 is marked, mark Q0 and Q2. For Q1 and Q2, Q1 input A is equals to Q2. Q2A is equals to Q3. Since Q2 and Q3 is marked, mark Q1 and Q2. So the final table, as we can see, all pairs are marked, which means no state can be merged. So the DFA already minimal with 5 states. So let's take a look with our minimized DFA. There are no changes before. So we have 4 states and 3 accepting states. These accepting states are Q0, Q1, Q2, and Q3, and another reject state which is Q4. So input epsilon, Q0 return, input A goes to Q1, another input A goes to Q2, input A goes to Q3, input A goes to Q4, and input A will return to Q4. So our final thoughts. Based on the Myhill-Nerode Theorem analysis and the table filling method language of our example, epsilon, A, double A, triple A is regular. So the minimal DFA requires exactly 5 states with no possibility for state reduction. This confirms that finite languages are always regular, as demonstrated by our ability to construct a complete DFA that precisely recognizes this language. So again, my name is Josh Kovic Fermano, and thank you for watching this video.